All right. So today's the last tute for physics. Yeah. Well, so today we'll go over just revised electricity, optics, and radiation. Okay. All right. So number one, we have an uncharged conductor A, which is brought into contact with a second identical charged conductor, which is B, and then the conductors are separated. Which one of the following statements about the charge on each conductor after separation is true? Okay, so let's draw this out. So initially we have two conductors, so just these boxes here, okay, and one of them is charged, so conductor A is uncharged, so there's no charges, and then the other one, let's say it's positively charged, okay, so it could be positive, could be negative, doesn't matter. Okay, and then next they're going to come into contact. Oops. Okay, so when they come into contact, what's going to happen to the charges? So they're both conductors. Well, these positive charges don't like to be next to each other, so the charges are going to spread out. Okay, so they're going to spread out evenly, like that. Okay, so now they're spread out evenly, and then now when you separate them, they're going to both have they should both have the same amount of charge. Okay? All right. Cool. And it doesn't matter if it was positive or negative, it'd still be the same result. Okay, so your answer would be option A. Number two, the diagram below shows an electric field produced by three charges. So we want to find out which statement is true. So first of all, if you have a positive charge, the electric field lines are going to go outwards from your positive charge. Okay. And then if you have a negative charge, the electric field lines are going to be directed in towards the negative charge. Okay? So that's the basic rule that you should always remember. Always goes from, so the electric field lines, they would go from positive to negative. Okay? So if you look at that diagram, the one in the middle, so Q2 has lines coming out of it. So is this going to be positive or negative? Yep, positive. And then so Q1 and Q3, they're both going to be negative. Okay. Now, the number of lines. So if you have two charges, and one's got more lines coming out of it, then that's going to have a bigger charge. So it means it has a bigger electric field. Okay. So if you have So let's say that you had two charges, and we'll look at this separately. So this one here has this many lines coming out of it, and then this one here has a lot more lines coming out of it. So that means that the one with more lines coming out of it this one has a stronger electric field, and so it's going to have the greater magnitude of charge. Okay, so you can see there that Q1 would have a greater magnitude than Q2, okay, and you've got two negative charges, so the sum would be negative. So your answer there would be B. All right, so we'll move on. So those were like pretty basic. Number 3, we have a circuit. So it's got a battery, a resistor, and a capacitor, and it's initially uncharged. Now, when you close the switch, the current is going to start to flow, and then over time it's going to decay. So after one time constant, so it starts off, the initial current is 100%, okay, and then after one time constant, it's going to decay to 37%. And then after two time constants, it's going to decay to 14%. And then after three time constants, it's going to decay to 5%. All right. So it would take two time constants for it to drop to 14%. So what you're going to do is you're going to find one time constant. So the equation for time constant is equal to RC. So the resistance is 1,000 ohms, and the capacitance is 10 microfarads. So you have to convert it into farads. So 10 times 10 to the negative 6 farads, and so that's 1 times 10 to the negative 2. Okay, so that would be one time constant. And then what you want is two time constants. So 2 times the time constant would be 2 times 10 to the negative 2 seconds. Okay, so that's the one that's the type of question that's come up the most. So for capacitors, that's probably going to be your most likely question. Okay. And then the follow-up question, how much energy is stored in that capacitor once it's fully charged? That's one they also like to ask a lot. So that's also really easy. So that's the electrical energy, which is the symbol U. So that's the symbol for electrical energy. That's equal to half CV squared. Okay. So half times the capacitance, which is 10 times 10 to the negative 6, times the voltage, which is 10. Okay. And that will give you 5 times 10 to the negative 4 joules. Okay. Right. Next we have number 5. A charge of 0.5 coulombs is moved from A to B and then back to A again along the path shown through a series of equipotential lines. So we want to find out the total work that must be done against the electrostatic field in order to move the charge along this path. So it goes from A. So here's your, it goes from 0 volts up to 10 volts, 20 volts, 30 volts, 40 volts. So it goes from 0 volts up to 35 volts, and then it comes back again. Okay, so if you remember, I said that what we're only interested in when we talk about work is the starting position and the finishing position. So in this case, it's finishing up where it started. So essentially the distance that it's moved is 0. Okay, so if the distance that it's moved is 0, work is equal to force times distance, and since the distance is 0, your answer is going to be 0 joules. Okay, and the reason for that is that you're going to put work in. So you're going to put work in to move the charge here, but then when you come back the other way, it's just going to be the negative of that work. Okay, and so that's going to cancel it all out. All right. And that's quite an important thing to keep in mind, because whenever they ask about these the work and distance questions, they like to have them go like a certain distance and then come back. Okay, so you're only interested in the starting and the final position. Number 6, we're moving on to optics. David wonders if there's life on Mars. He plans to send signals to Mars by flashing his flashlight and hoping for a response. When David sends a signal, Mars is located about 75 times 10 to the power of 6 kilometers from the Earth. How long would it take a light pulse to travel from the surface of Earth to Mars? And we want that in minutes. Okay, so first of all, we have the distance. So that's 75 times 10 to the 6 kilometers. So we have to have that in meters. All right, so that's going to be another 10 to the 3, right? So that's just going to be 75 times 10 to the 9 meters. Okay. And then what we want to find is the time. And then since it is light that is traveling, we know the velocity of light in vacuum or air, right? So we know the velocity of light, that's going to be 3 times 10 to the 8 meters per second. Okay, so you have the distance, time, and velocity. Time is equal to distance divided by velocity. So that's 75 times 10 to the power of 9 divided by 3 times 10 to the 8. And that will give you 250 seconds. And then divide that by 60 to get that in minutes. And that will be 4.2 minutes. All right. Number 7, we have a diagram of a concave lens, and the object is located inside the focal point. All right, so a concave lens, you have to first determine whether that's converging or diverging. Okay, so if it's a concave lens, it's going to be diverging. Okay. And if it's diverging, then that means the image is always virtual, reduced, and upright. Okay, so that doesn't matter whether it's inside or outside the focal length. Okay, so you should have those, unless you're confident you can remember them, you should have those rules written down. So for diverging, it's always virtual, reduced, and upright, regardless of whether it's inside or outside the focal length. Okay, and then if you have a converging, then it's going to depend whether it's inside or outside the focal length. But if you look at my cheat sheet, which I have on my Google Drive, it's got the rules on there, so make sure you either remember it or you write it down. Right, so then number 8, we have a 3 meter high object which is placed 200 meters from your eye. What is the size of the image of this object on your retina? And assume that the lens to retina distance is 2 centimeters. Okay, so first of all, we have the height of the object. So that's 3 meters. And then the distance of the object is equal to 200 meters. And then we want so if they ask about the size of the image, that's going to be the height of the image. So we want to find out the height of the image. And then we want, so then the lens to retina distance is where your image is going to form. Okay, so if you think of the eye, here's your eye, and then you have your lens at the front of the eye. So that's the lens at the front of the eye, and then there's the retina at the back. So the light comes in, and the image is going to always be a real image that forms at the back of the eye. So the distance from the lens to the retina is your DI. So this distance here, that's your DI, and that's equal to 0.02 meters. Okay, so that's an important connection to make whenever they tell you the lens to retina distance. That's the DI. Okay, so now we have our variables. So the equation that we'll use is HI over HO is equal to negative DI over DO. And so what we want is HI. So we're just going to move HO up here. So times HO, and this can go away. All right. So it's the negative DI, which is negative 0.02, times the height of object, which is 3, divided by DO, which is 200. And that will give you negative 3 times 10 to the negative 4 meters, okay, which is, so turn that into millimeters, which is negative 0.3 millimeters. Okay, so why would the height of the image be negative? Yep, so because it's upside down. Okay, so it's going to be a real image, and a real image is always inverted. Okay. So if I draw a lens here, and here's your object. So a real image will always be inverted, okay? and a virtual image is always upright. Okay. So number 8, we have the radius of curvature of a convex mirror, and that's 2 centimeters. If the object is 10 centimeters to the left of the mirror, where is the image created by the mirror in millimeters? Okay, so first of all, the radius of curvature. So what we have here is we have a convex mirror. Okay, so if our So our object is here, okay, and then our mirror, it's a convex mirror, so it's going to be like this. Okay, so this is our convex mirror, and what the radius of curvature is that if it was a complete circle, this length here, that would be the radius of curvature. And then, so how is the focal length related to the radius of curvature? Yep, so the focal length will be halfway between, half the distance of the radius of curvature, okay? So the focal length is equal to the radius of curvature divided by 2. Okay, so what we're told is that the radius of curvature is 2 centimeters, so the focal length must be 1 centimeter. Okay, so this distance here is 0.01 meters. And that's going to be your focal length. But then you have to think about whether this convex mirror is going to be converging or diverging. Okay, so if it's a convex mirror, light's going to come in and it's going to bounce off like this. Right, so these light rays are diverging from each other. So there's so this is going to be a diverging mirror, and if it's a diverging mirror, your focal length is going to be negative. Okay, so our focal length is going to be negative 0.01 meters. Okay, and that's very important, otherwise you'll get the wrong answer. All right, so we've got the focal length, and then we know what the distance, the DO is. So the distance of the mirror to the object is equal to 10 centimeters, which is 0.1 meters. And what we want to find out is the DI, so where the image is located. All right, so we're going to use this equation. The focal length to the negative 1 over the focal length is equal to DO to the negative 1 plus DI to the negative 1. And since we want DI, that's going to be DI to the negative 1 equals F to the negative 1 minus DO to the negative 1. Okay, but here we just want DI, not DI to the negative 1. So you put brackets around here and then make that to the negative 1, and that gets rid of the negative 1 on this side. Okay? Cool. So we're going to have focal length, which is negative 0.01 to the negative 1 minus DO, which is 0.1 to the negative 1, bracket, and then all of that to the negative 1. So that will give you negative 0.009 meters, which is equal to negative negative 9 millimeters. Okay, so if it's a negative DI, that means that it's a virtual image. Okay, so for mirror, a virtual image is going to form on the opposite side as the object. Okay, because a real image has to form on the same side because the light rays are coming back. Okay, so a virtual image would form on the opposite side of the mirror as the object. So our image is going to be located on the opposite side, which is to the right of the mirror. Okay, so your answer is going to be B. And keep in mind that it's the opposite rules for a lens. Okay, so if it's a lens, so I'll write this down because this is important. So for a mirror, real image forms on the same side as the object, and a virtual image forms on the opposite side as the object. And then for a lens, a real image forms on the opposite side, and a virtual image forms on the same side. Okay? All right. Number 9, we have the wavelength of light in air, which is 532 nanometers. And we want to find out the wavelength when it goes into seawater, and that's in nanometers as well. And we've been given the refractive index of seawater, which is 1.34. So for the refractive index, you can use the velocity of light, or you can use the wavelength of light. Okay, so remember that the refractive index tells us how much the light's going to slow down when it enters a different medium. And when it slows down, because the velocity of a wave is equal to the frequency times the wavelength, the wavelength of the wave will also slow down, the wavelength of the light. Okay. So the equation that we're going to use is the refractive index n is equal to the wavelength of the photon in vacuum or air, and that's divided by the wavelength in that medium. So in this case, the refractive index of the seawater and the wavelength in the seawater. Okay, so we know the refractive index, so this is what we're trying to find. So the wavelength in the seawater is going to be equal to the wavelength in the vacuum or air over the refractive index. So we've rearranged that equation. So that's going to be 532 nanometers divided by 1.34. Okay, and since we want the answer in nanometers, we don't have to convert it in this case. And that's going to give you 397 nanometers. Okay. Number 10, barium emits gamma radiation with an energy of 662 kilo electron volts. What's the momentum of each of these gamma photons? All right, so remember that if you have a photon, it's got 4 properties. So a photon, it has energy, it has frequency, it has wavelength, and it has momentum. Okay, so if you know any one of these 4, you can find the other 3 using your equation. So on my cheat sheet, they're just on the top line of the radiation piece of paper. Okay, so make sure you have those equations. All right. So in this case, we want to convert energy into momentum. So the equation for that is momentum is equal to the energy divided by the speed of light. Okay. And the energy in this case is in electron volts. So that's 662,000 electron volts. So 662 times 10 to the power of 3 electron volts. But in order to convert it, we need that energy in joules, not electron volts. Okay, so to convert, so 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. Okay, so that's important to remember as well. Make sure you've written, oh well, it's on your cheat sheet anyway, but yeah. So 662 times 10 to the power of 3 times 1.6 times 10 to the negative 19. So that's turning our energy into joules. And the speed of light is 3 times 10 to the 8. And that's going to be 3.5 times 10 to the negative 22. Okay. Sweet. Number 11, we have an electron, which is initially in an atomic energy level of EI, jumps to a lower atomic energy level of energy EF. When the electron makes this transition, the atom emits a photon with a wavelength of 1.73 nanometers. Okay, so what's happening here is we have our nucleus, and then we have our energy levels. Right, so we don't know the numbers, but let's say this is n equals 1 and n equals 2. Okay, so our electron has jumped down to a lower energy level. So there's going to be a change in energy, right? Because remember that this is the lowest energy level, this orbital here. And then as you go outwards, the energy is going to increase. So the energy of the electron has decreased, which means that the energy has to go somewhere, and that's going to be emitted as a photon. Okay, so we've got a photon that's been released, and we know that the photon's going to have energy, and we know that it will have a wavelength. Okay, so the wavelength of that photon is 1.73 nanometers, and we want to find out what the momentum is going to be. Okay, so the equation for that is momentum is equal to the Planck's constant h divided by the wavelength. So Planck's constant is 6.63 times 10 to the negative 34. And that's divided by our wavelength, which is 1.73 times 10 to the negative 9. And that will be 3.8 times 10 to the negative 25. Okay? And then number 12, we're looking for the difference in energy of the two atomic energy levels. Now, there is an equation that you can use to calculate the difference in energy between energy levels, but in order to do that, you need to know the n of the energy level that it started off in, and also the n of the number of the level that it's dropped down to, but we don't know that in this case. And the other thing that you also need is Z. So Z is the number of protons in this nucleus. That's the atomic number. But we don't have that either. So we can't calculate the change in energy of the orbitals using that equation. Just to jog your memory, that's this equation here. So delta E is equal to Z squared NF to the negative 2 minus NI to the negative 2 times 13.6 times EV. Okay, so that's the equation that you can use to calculate the change in energy levels if you know the number of protons and the number of the atomic energy levels that they move to. Okay. But what we can do is we can calculate the energy of the photon, because the energy of the photon will be equal to the change in energy. Okay, so the energy of the photon is equal to, so we can use either the wavelength or the momentum. So let's just use the wavelength. So that's h times c over the wavelength. And so on my cheat sheet, I just have h and c multiplied together, and that's 1.989 times 10 to the negative 25. And the wavelength was 1.73 times 10 to the negative 9. Okay, and that's going to be 1.14 times 10 to the negative 16 joules. Okay. So also if you want to use the momentum to calculate the energy, the equation is energy is equal to the momentum times the speed of light. Okay, so that's your other equation to turn momentum into energy. So number 13, we've got we want to know which one of the following particles will be produced in the decay of radon, I think, into polonium. Okay, so what you're going to do is you're going to look at the top numbers, which is the mass number. Okay, so it's going from 222 to 218. So that's decreased by 4. Right. And then the bottom numbers going from 86 down to 84. So that's decreased by 2. Okay, so what you've got is you've got this thing here being produced, which is an alpha particle. Okay, so an alpha particle is 2 protons and 2 neutrons. Okay, so remember that the top number tells you how many nucleons there are. So that's the number of protons and neutrons. All right, so there's 4 nucleons, and the bottom numbers tells you how many protons there are. Okay, so it's important to remember that because in past exams they have asked you, like, they'll just give you like something like this one here, and they'll say, how many neutrons are there? How many neutrons are there in this atom here? Okay, so then the number of neutrons in here, so that's this number of nucleons, this number of protons. So the number of neutrons would just be 218 minus 84, right? So just keep that in mind. Number 14, you're studying a radioactive isotope which has a half-life of 2.4 days. You have a pure sample of this isotope, and note that it has an initial activity of 6 millicuries. Okay, and you want to find out what the activity of the sample will be in 1.2 days. So here we've been given the half-life. So the half-life is equal to 2.4 days. And the time that passes is equal to 1.2 days. And also you know that the initial activity, AO, is equal to 6 millicuries. Okay, so we want to know the activity after a certain time. So that's this one here. All right. Now we want the activity in 1.2 days to be in millicuries, which is the same unit that we've been given. So we can just leave that unit as it is. So here's our equation. Okay, so we need the decay constant, right? So we need to calculate what the decay constant is going to be. The decay constant is equal to 0.693 divided by the half-life. Okay, so when we have the half-life and the time, and they're both in days, we can leave the half-life in days as well. So remember that normally you're going to have to convert the half-life into seconds when you calculate the decay constant. So we can leave it in 2.4 days. Or we can leave this as days because we're going to, when we put in the time, we're also going to put in time, days. So that's going to be 0.28875. So we've got the decay constant. Initial activity was 6 millicuries times E. So E is the button on your calculator, and you get it by pressing Shift LN. So negative 0.28875 times the time, which is 1.2 days. So we'll leave it as days. And that will be 4.2 millicuries. All right. Number 15, so this is carrying on from question number 14. It's the same question stem. How many moles of the radioactive isotope are present in the pure sample of the isotope before it decays? So now we want to know how many moles there were in that sample before it decayed. All right, so what you need to do is you need to find out the number of molecules that we had, and then once we have the number of molecules, we can convert that into moles. Okay, so remember that big N is the number of molecules, and little n is the number of moles. Okay, so don't get confused. They're two different things. All right, so first of all, we have to, so the equation that we're going to use is A is equal to the decay constant multiplied by the number of molecules. Okay, so A is the activity. So we know the activity. That's going to be the initial activity of 6 millicuries. And what we want to get is the number of molecules. So the number of molecules is equal to the activity divided by the decay constant. Okay. So we're going to have to calculate the decay constant again, because last time we calculated the decay constant, we did it in days, and this time it has to be in seconds. Okay, so that's 0.693 divided by the half-life. Okay, so this is the half-life in seconds. So that's 2.4 days. So 2.4 times the number of hours in a day, which is 24, times the number of seconds in 1 hour, which is 3,600. Okay, so that's 2.4 times 24 times 3,600, and that will give you 3.342 times 10 to the negative 6. So that's your decay constant. Okay, so now so the number of molecules equal to activity over the decay constant. And so the activity, that was 6 times 10 to the negative 3. So 6 millicuries is 6 times 10 to the negative 3 curies. And we have to turn that into becquerels as well. So becquerels is the correct unit for activity. So that's going to be 6 times 10 to the negative 3 times 3.7 times 10 to the 10. Okay, so to turn curies into becquerels, you times it by 3.7 times 10 to the 10. So you should have that conversion on your cheat sheet as well. And then your decay, so that's over your decay constant, which is 3.342 times 10 to the negative 6. And that will give you 6.643 times 10 to the power of 13. So that's the number of molecules or atoms. So you can call them molecules, atoms, or the number of nuclei. It's all the same thing. And so once you have that, you're going to find the number of moles. So the number of moles is the number of molecules divided by Avogadro's number. Okay, so the number of molecules is 6.643 times 10 to the power of 13. And Avogadro's number is 6.02 times 10 to the 23. And that's 1.1 times 10 to the negative 10 moles. All right, so that's option A. So a bit of a mission. Yes, and hopefully you don't get one of those. All right, last one. Number 16, we have a 70 kg nurse who's accidentally exposed to a total of 7 joules of X-ray radiation. What absorbed dose does the nurse accumulate? Okay, so absorbed dose is simple. It doesn't take into account what sort of radiation it is. It's just the amount of energy that's absorbed by the mass. Okay, so absorbed dose is equal to energy in joules divided by the mass in kilograms. So our energy was 7 joules and our mass is 70 kilograms. So that's going to be 0.1. So 0.1 gray of absorbed dose. And then, so we want that to be in rads. So 1 gray is equal to 100 rad. So we need to turn gray into rads. So we're just going to multiply that by 100. So that will give you 10 rad. Okay. So we'll start again in 10 minutes at 8:30. All right. Cheers. This is still on. Let's turn it on.